Okay. Cool. Okay. Thank you for your attention. Hello. Okay. Sorry, things are going a little late. My computer was acting up, but okay. So lab 1 seems like people are doing a really good job so far. Quite a few people have been checked off already. A lot of people though are running into a lot of problems just setting things up. And it's like you follow the steps perfectly and then nothing works. That's what the TAs and tutors are there for. Highly recommend allocating times for you to go in and ask questions. We're in the process of also like rewriting some of lab 1 to be a little more helpful. None of the like requirements will change, but it's still a draft right now. If you wanted to look at our draft as we're working on it, then you can do so. I'll quickly show you how you can find that. So there may be, you may find it useful, may also be a waste of your time because it is a draft and we'll post it like officially later. But so here's the homeworks, right? All homeworks. And right here is the pull requests tab. Let's keep our voices down. So when I open pull requests, you can see that Bradley, the TA, worked really hard and rewrote a lot of lab 1 to be more helpful. So you're welcome to take a look at his changes. But before we merge it into main, we just need to fix some typos. So, yeah.
I was like wondering when will the assignment be available to turn in on grades?
Oh yeah, so a TA I think is working on it right now. Should have been available already, but hopefully by the end of the day. Yeah. And so I will mention something that will happen as we're still getting kind of organized. So what we will do is we will post every single assignment onto Gradescope like this week, so you can submit at any point, like from now on until the end of the quarter. And the purpose of that is actually the TAs will not be checking you off onto like a spreadsheet or anything. Instead, what they will do is they will go into your Gradescope, the PDF, your report submission, and they will grade your report right in front of you. And that will be what your grade is. Now, hopefully, just you do the report and it's perfect and 100%. If they see like, hey, actually, I need you to write a little bit more for that, they'll tell you, and then you can go and change it, and then you come back to them, and then they can raise your score back up. So that is how checkoffs will work, is you will need to like present your code actually working, and the TA will then grade your project report right in front of you. Okay, that is how it is going to work, at least once we get the Gradescope submission boxes all open. Yeah, and it's a slightly different mode that the TAs have not like grown used to yet. So in case someone like pulls up a spreadsheet and then marks you off, maybe go and be like, actually, Ethan told us in class you were going to grade us on our Gradescope submission. Maybe go and just remind them that because they may have forgotten because it is a new thing. So okay, good. Feel okay? So yeah, because the point is that we want you all to get just 100% on everything. So we want there to be like back and forth. And it's like, oh, like, why did I get half points on this lab report question? It's like, oh, well, you can change this thing and then we can increase your grade and now it's better. Yeah, that's the point. Okay, so just wondering, how many of you are like mostly done with lab 1, would you say? Oh, this is wonderful. Okay, great. Okay, I won't spend too much time on lab 1. Any questions on lab 1? Yeah.
For the lab report, it says that we have to do the edgy room. Do we still have to do that even though we have the pipeline?
Actually, yeah, so that is something that's changed. You don't need to do the edge room part. You can just use the access point that is in the lab. Yeah. On Canvas, I posted tutorial, or at least the SSID and password for the wireless access point that is specific to this class. So you don't need to get Eduroam working on your Raspberry Pi. Instead, you can just connect to that wireless access point, and it should make things easier for you. And this goes for like all future labs. Yeah. Okay. Good question. Cool. So now I wanted to talk a bit about Lab 2, which will be due next Friday, not this upcoming Friday. Anyone start Lab 2 yet? Okay. Oh, cool. Excellent. Okay. So, yeah, it's pretty good. So the first part of Lab 2 is all about debugging. using GDB. And I wanted to kind of walk through the kind of like maybe our train of thought and like how we would go about debugging a microcontroller. Okay, so here is our ESP32. And so has anyone taken like an analog circuits class where you needed to like build stuff on a breadboard or, right? Okay, sure. And did you, I'll just, there we go. Okay. When you needed to debug like a breadboard circuit, what would you usually do? Maybe you'd like plug in a voltage monitor at points or something. Maybe you would plug in like an oscilloscope when using an oscilloscope. Yeah, so that's kind of how like analog circuit designers will debug things, right? Is they will have actual like wires that they can connect like a probe to, and then they can read out that monitor. They can read out that voltage level. And there are like very complicated like digital circuit analyzers that you can buy that are like $1,000, maybe like a few hundred probes on them, where you can connect up maybe like a 64-bit bus. So maybe if you have like 64 wires, you can go and connect all of those 64 wires to your digital analyzer. But let's say now on our microcontroller, right? Now let's say we wanted to debug maybe like the internal registers on our microcontroller. Okay. Well, there's a big problem in that, well, there's a big like kind of like package surrounding this circuit. So we're not able to go and like probe the things that is inside of this microcontroller, right? It's all like, it's in a package. And even if we could, even if this was just like bare wires, like all these wires would be extremely small. And like, you know, they do actually have like super fine probes, like hypodermic needles that you can rest onto pads that are just like a micron across. And in my undergrad, I took like a tape out class where we went into a fab and we had to like, actually put like a tiny, tiny little probe, which was almost just like a hair of like tungsten or something. You just put it onto this like super tiny wire, and then you could read out the voltage at that transistor. And it was like super cool, but not really practical for like if you were mass producing microcontrollers. Like you can't also expect to be giving out like $1 million machine to like probe super tiny little signals. So okay, so what do we do instead in order to debug our microcontrollers? Yeah.
Serial out.
Sure, so absolutely. So we can use serial out. We can use like UART where you do printf, and you can just add some like print statements and stuff. That's pretty good, right? Maybe a downside of that though is now you need to like put a bunch of print statements all over your code. What is like the main way that we debug code like in the world? Like do we just put print statements everywhere? Like maybe we do, but probably the better way is to use like GDB or something like a debugger. Something that you can actually like single step through every single instruction that is running on your computer. Anyone use like a debugger? Okay, yeah, okay. So yeah, the point of a debugger is you have some sort of software application, and yet you can run like a single line of code and see how that affects your entire program. And then if you want, then you can go and run the next line of code. Or if you want, you could run like continuously until you meet like a certain a specific line of code or a single expression like evaluates to true. The purpose of this is for testing reasons. It's like if I ever wanted to test if like a variable becomes invalid, then I could add a breakpoint and it's like, oh, is this variable ever invalid? So okay, well if I now wanted to debug this microcontroller, well yeah, there's an issue. It's that, well on each of these pins, right? Like if we have a 32-bit like program counter inside of this, right? This is probably a 32-bit program counter. If you think back to CSE121. Well, there's not like 32 pins that we can just read out the program counter to. And there's this big package in the way, so we can't put like our super fancy like $1 million like probing machine onto this. So okay, in that case, what do we do? How can we somehow read out the program counter and read out all of the registers of our microcontroller if we can't just read it out on all these GPIO pins and we can't use like a probe? What do we do? Yeah. Okay, wait. Go and chat with the person next to you. Maybe discuss for a second. It's like, how do you access all of like the individual wires and transistors inside of this? Like, how do you access the program counter and the registers and things? But go and chat. Okay. Anyone know what these symbols are? They're not clocks. Well, this is a clock right here.
Registers.
Yeah, these are registers or flip-flops, yeah. So if we imagine that maybe we only have like a 4-bit program counter, right? Maybe somewhere inside of our massive microcontroller, like of the like thousands and thousands of flip-flops that are inside of a microcontroller, maybe there are like 4 specific flip-flops that we want to access inside of this microcontroller. Well, there is a really cool standard that was created under IEEE, and this standard is called JTAG. Oh. And I don't know what JTAG stands for, but there we go, JTAG. And I'm not a JTAG expert, but I'll just give you kind of a brief idea. The idea is that there are little extra bits of hardware that are actually put into microcontrollers, but almost all microcontrollers support JTAG, where there's maybe just some sort of like extra little like way to read out each of these flip-flops. And then it is put into some like big kind of black box. And then there is some way to access this. So now you can just put in like some sort of either like address, or you can put in something that can actually read out any flip-flop that you want from the microcontroller. Like not every microcontroller here. This is like the PC. We call this like a JTAG interface. Maybe this would be over like USB. These are like the JTAG probes, and then there's USB communication. And so now, like baked into like almost every single microcontroller that you will find, like ATU Mega, ESP32, STM32, all of them support JTAG in some way, and they will let you read out some of the most important flip-flops. So for example, your program counter, or maybe like specific banks or things. And this entirely is just for debugging. And actually, most of the time, this is like disabled. And in most like CPUs and things, like even like CPUs, like even like the Apple like M series processors will even have JTAG inside of them. But what they will generally do is maybe they'll have some sort of like fuse inside of their circuits. That means that like it's like, all right, like great, like I have finished testing this chip. Maybe they runs through an assembly line like after the chip has been designed, and then it runs a bunch of tests using this like JTAG interface. And then after it's done running all of the tests, then what it'll do is it'll blow all the fuses right here so that now like no longer this can be used anymore. Pretty sick. Yeah, so now like if you're Apple and you are trying to obfuscate your hardware design because you don't want someone to come along and steal it, now you can just blow all these fuses, and now all of a sudden JTAG is like permanently disabled in hardware. You know, it can read out all of like the mysterious little like bits and bobs, like your proprietary Thunderbolt controller or something. So cool. Okay. Yeah.
How does it work if you have like multiple threads running?
Multiple what?
Like one thread is like has JTAG active, but the other threads doesn't, or both threads do have.
So there's no like concept of threads. All JTAG does is it just can read out basically your flip-flops. So I guess if you have like multiple cores on your PC, then that would just be like different addresses. Like you say, give me the flip-flops in core 2, or give me the flip-flops in core 12.
But like if you had multiple threads running on the same core, would you be able to read the like program counter of the other threads inside like the JTAG like memory?
Oh, sure. So you're asking. Correct, right. So if you have like a program running on these flip-flops, and then they go and context switch to like your bank account information or something, now your like confidential bank account information is now put into these flip-flops, then yeah, JTAG would still be able to read this out.
Oh, okay.
Right. Yeah, because JTAG, it doesn't really, at least I believe, it doesn't really take into account like threads. All it does is just kind of read out the hardware that's embedded in the device. Yeah. So yeah, that's another reason why maybe JTAG isn't a good thing to keep around on like your devices in production. Yeah. Sure. Okay. Cool. And yeah, like I said, not really a JTAG expert, but that's okay because a lot of people are, and there are lots of great like abstractions that we can take advantage of that use JTAG. And the first thing that like you will be gaining experience in is using GDB to actually debug our microcontroller. Because usually like when you run GDB or when you run debuggers, you end up debugging like the code that is running on your computer. But it's kind of interesting because what we can do is we can actually debug the code that is not running on our computer, but is actually running on our microcontroller. So we can use JTAG to read out all the program counters and all the registers and things. And GDB will be able to like use the JTAG abstractions, and then it will make it seem like we are debugging the code that's on our computer. It's actually a JTAG. So yeah, okay, I was gonna go through kind of roughly how to get started doing that today. So this is kind of the first part of your lab 2. So that's what I'll be spending kind of the rest of the class on. Any questions? Yeah.
I was gonna ask, what's the benefit of using JTAG versus emulating a single system like this?
Oh, sure. The question was, what is the benefit of using JTAG versus just emulating an entire emulating ESP32 just on our computer? Yeah, any ideas? Yeah.
It's what the actual hardware is doing instead of an emulation.
Yeah, exactly. Like what if the emulator has some bugs or something? Like this is the actual hardware. It's nice to know.
Also, when you get like very, very large chips, sometimes emulation takes multiple days.
And yeah, that's kind of the main thing. So emulating circuits takes forever. Like if you want to design a CPU that can boot Linux, it could take like a week potentially to like actually boot into Linux before you actually know it's like, oh, did this work or not? And then you get into Linux and then you realize, oh, there was a bug or something. Then you have to restart it. Yeah, but actual hardware will run extremely quickly. And there will be some performance penalty, I believe, due to JTAG. I'm not exactly sure how that works. But debugging your microcontroller does take a little bit longer than running it in non-debug mode. Yeah. Another question?
I was going to say the hardware almost always behaves differently than even the most perfectly written emulator. And also inputting, say, analog signals into the emulator is going to be a challenge.
Sure, absolutely, yeah, analog signals. Yeah, I'll leave it at that. But yeah, debugging microcontrollers is very important. So cool, okay. So this is lab 2. So you can see it is due next Friday. And so you are provided just this file, but you were also provided this lab2 debug elf file. Okay, anyone know what an elf file is? Anyone seen ELF files before? So ELF files, this is probably like very important. You all should just know this throughout your life. An ELF file, so it stands for executable and linker format. This is just what compilers will compile to on Linux. So this is the like file that Linux is expected to read in order to find like source code that has been compiled down. So this is actually like when you run an application on Linux. If you were to open up the file, you would see that it's like actually a .elf file, even if it doesn't actually have this .elf extension on it. So ELF, this is just like compiled down code. So okay, so if this is compiled down code, then what you can probably imagine is this whole file started out as probably like a C file, and then it was compiled into this .elf file. And the goal of this assignment, at least this part, is to debug this file, so put it into the debugger, and then watch exactly like what instructions are being run to try to kind of reverse engineer what this program is. Because you're not given the C code, but you are given like all the assembly instructions in this .l file. Okay, so first let me go and download this file. So to download the file, you can see it's under lab 2, and here it is. So if I open this, and if I click on view raw, then you can see it downloads it. But what I will do instead is I will right click on it and I will copy this link, because what I want to do is actually download this from command line, because it'll make my life a little easier. So I'm going to copy this, and then 1 second. Okay. There we go. Okay. So here oh, delete this. Sure. So here I just have like the Blink example pulled up from ESP IDF. It's kind of just helpful to stay in the ESP IDF examples, unless you have like a really good reason to pull it out. You could just make a copy of this, and then that's where all of your labs are. But okay, what I'll do is, actually want to out of all that. Okay. Good, loading up. So I'm going to CD into this Blink directory now. Copy this. CD that. And now if I want to download this this file, so I'll copy the link again. So copy. And then I will type in wget, and this is like website get. So I can go and fetch this .l file, and now this will download it. There we go. So now I have this this L file right here. If I try to open it, so I just opened it. Notice that it's opening it in my hex editor that I have installed. And we can see this actually, the first few bytes right here stand for, they say ELF, which is kind of fun. So we can see that this is, like generally like in most files, when you open them up, the first like 4 characters will show you additionally what the file type is. This goes for like zip files as well, and like PNG files. If you ever open up the file in like a hex editor. Yeah, it's because, I mean, this is a hex editor because we can see like every single hex value inside of this file. And then on this side, we can see here it is just trying to interpret all of the bytes as if it was like actual ASCII data. This is what it would look like if we tried opening it in like a text editor, versus here we're actually seeing all of the different bytes and things. Yeah, anyone seen a hex editor before? Okay. Yeah, so hex editor, very cool. If you ever want to see like just what goes into actual files. Like if I want, I can open up like this file as well, like the C file in a hex editor. And you can see, so here's all the text. But here is the actual, like here are the actual values that go into the hex like code for it. So we can see all the different character encodings for each of these. Yeah, kind of cool. Okay, hex editors. And hex editors are great, yeah, when you don't have like code to debug. Instead, you just have like all these like 1s and 0s. So if we scroll around, you can see most of it is 0. Then, okay, well, it looks like there's some parts that it's like there's text, but like, is this text? Yeah, okay, it looks like this is text. And, okay, well, actually, this looks kind of random. So my guess is maybe these are actually like the assembly instructions that go into the computer. Like maybe this right here, maybe this denotes an instruction that will be able to be read by the ESP32. So when you like dump the file in, like this is the actual instruction. But it's not very readable, right? Like imagine this was like a quiz question. It's like, all right, given, you know, these random numbers, it's like, what instruction is this? It's like, yeah, I don't know, it's kind of hard. Well, what you can do instead of just like looking at the actual hex value is instead you can run a obj dump on it. So right here, obj dump. Object dump. What this will do is it will print out all of the different instructions in this file in like a human readable format. So I'm now going to copy this command. And I will run this. And you can see it's using RISC-V64 unknown ELF obj dump. I believe this was pre-installed by the ESP32. I believe, like when you do like the .install.sh. So yeah, and this command was provided to you in the lab instructions. And so now I can open up this human readable file that shows you everything that goes inside of this elf file. And so, okay, so cool. So now we can see actually like all the different instructions. So now this makes a little bit more sense. So, okay, so cool. We have these instructions and you can scroll down more and okay, it's a lot of instructions. It's like, yeah, crazy. But so these are actually all the instructions that make up this file. And if we want, we could now just start going like line by line and trying to understand this massive 100,000 line assembly file. That's probably not the best way to do it. Okay, so if you were to start debugging this file, or it's trying to reverse engineer it, then what is probably the best way to just start like getting into this file? Like what is the first place to start? Yeah.
I would look for the entry point, the main.
Sure. So yeah, so every ELF file will have some sort of entry point that tells us like what instruction it's going to start running at. And do we remember what the like main function is called on ESP32 programs? I think it's at main. Yeah. So if we just look for maybe at main. Oh, look at this. Okay. So potentially, let's keep our courses down. Thank you. So potentially, this is probably where it actually starts running all different instructions. So like when we load up our ESP32, these are the actual like first instructions that begin running. So okay, cool. So we've got like add I instructions, then doing store word and another add I. Actually, does anyone know what these instructions are? The purpose of these are? What is that? Yeah, it's stack pointer, right? It looks like it's just like allocating some memory on the stack. Maybe it's like allocating for all the stack variables. Maybe it's pushing like the return value. Not sure exactly what it is. But yeah, so this is just all stack related things. And then, yeah, okay, but then it starts doing other stuff. And well, I was hoping this was going to be more kind of readable, but honestly, it's still a little like kind of hard to read, right? We just have all these random jump instructions here. And yeah, jump and link. So it's kind of hard to know like what is actually happening. Okay, so this is where GDB can be very helpful because maybe instead of like trying to understand every single line of assembly here, maybe the first step is just to see like what lines of assembly are actually even run. Like here we have a brunch equal to 0 instruction. Like I don't know if this is equal to 0, so like I don't know where this program is going. So it would be just much better to see like what instructions are actually even being run in the first place. So okay, like I said, we can use JTAG to get the ESP32 debugging. So I'm going to quickly show you how to do that. And this is explained in your lab document, but the lab instructions can be a little bit confusing. Okay, so yes. Okay, so the first thing that you'll need to make sure you have is open OCD running. You may need to install this separately. It could be a little bit challenging just to get like this line of code working, but hopefully we can hopefully for this example, it will be seamless. So I'm going to run, oh, actually that won't work because I need to connect my ESP32. Okay, any WSL users who have used this script yet? Okay, cool, got one. Yeah, so I highly recommend actually moving away from the Raspberry Pi for future labs. So if you're on WSL, then you will need to get this script working. I posted it on Canvas. Okay, so good. So now, in theory, this should be working. It's still not working. Right, because so yes, I think I ran into this issue a while ago. So the issue that we're getting right now is this is potentially an issue that you will get. I'm showing you how to debug all of these like individual steps. So this issue is that you don't have the correct permissions, or at least I don't have the correct permissions set up for my ESP32, and I don't remember the command off the top of my head. But what I did do ahead of time is I just asked ChatGPT. Basically, I just like put this this whole command into ChatGPT, and then it gave me the correct command to fix the permissions error. So I'll say, can you and I will zoom in a bit. Oops. Okay. Also, quick note on ChatGPT. So what I find is that if you paste in like a really long code block or a really long error block, it seems to forget by the time, like if you ask it something at the front, if you're like, oh, can you help me fix the permissions? And then you post in like this really long bit of code after that, it usually will actually completely forget that you even asked it a question. I don't know if any of you have experienced that. So what I always like to do is I always put the question actually at the very end. Or I'll like start it. I'll be like, yeah, can you help me fix the permissions error? And then I'll go and just like paste the exact same question again. Okay, so let's see what it says. Hopefully it's kind of quick. Yeah, good. Okay. And I actually don't like any of these. Can you, let me see. So personally, I like to use chmod, and so chmod, this will modify the permissions like directly in a single like shell environment, so that when I go and like disconnect my ESP32, I don't have to worry about things like sticking around. So I'm going to say, can you use chmod instead? And hopefully this will work. Okay. Okay, let's go and double check that this command actually lists out our device. Okay, did not. I'm going to stop beating around the bush. I'm going to just paste in this command that it worked for me last time. So this is what ChatGPT gave me last time, which is really great. So what this is doing is it found that my device was like this file right here. It's linked to this file. So hopefully this works. Yeah, not going. Okay. Poop. Oh, that's right. Hold on. Aren't you glad that I'm the one debugging it in front of you instead of you guys later? You're like, how did he do that? Okay, that's right. So you can run ls-usb. That's right. So ls-usb, this will print all of my USB devices. And so now we can see that we have this device right here, expressive USB JTAG. Cool. So this is our ESP32. And we can see that it is on bus 0, device 7. So the issue was actually, yeah, we need to connect to device 7 here, not 6. So now, and I'm assigning 666 to this so that we can actually read and write from this. And so now there we go. So now I ran it. Now we actually have access to this port. Now what I can do, I believe, is run OpenOCD. There we go. Cool. So after all that, good. So now it's working. Any questions on that? Move faster. Okay, cool. Yeah.
WSL won't be able to see the USB unless you do that.
Correct. Right. You have to run the PowerShell script first. Yeah. Yeah. Question? Okay. Cool. So now that I have OpenOCD up and running, what that effectively means is now OpenOCD is like running a bunch of like JTAG things kind of behind the scenes for me. And I believe what it has done is it has opened up kind of like a hardware port for me to connect to using GDB. So now what I can do is start running GDB. And yeah, so we can find GDB if you ever are having trouble finding it. So what it is going to be is, so I can run RISC 532, now hit tab to autocomplete. There we go, so now we can see ESP ELF, and now if we type in GDB, and I'll type ls, oh, it looks like it still was not able to find that. Wait, what? This was just what? I think something weird happened. Okay, anyway, so I can just run this. There we go. So now we can see that we've successfully opened GDB. Notice that it says like ESP ELF, right? This is different from what you're probably used to, which is just typing in like GDB. And the purpose of this is considered like a cross-compiled GDB, meaning that it's meant to work not with the files like that run on your computer, but instead it's meant to run on files that are compiled for not your computer. And like if we also like look at the other programs that we had access to, so we have GDB, but we also have like G++ here, and we have GCC, and so all the kind of like standard kind of C++ tools that you get through installing like C++. There are all these different like ports of it that now work with the ESP32 using VersaCloud. So yeah, kind of sick. Okay, so GDB. Now if we want to actually open up this ELF file and start debugging it, then we can just go and copy this and open this up. There we go. So now I've opened up this file. You can see that it has loaded everything. Now, in order to actually get GDB, so we're running GDB, but in order for it to actually be able to read this ESP32, the next thing that we need to do is connect to this by pasting in this command right here, target remote and 3333. This is provided to you in the lab instructions. And yeah, what this will do is it will like set up the JTAG communication. So there we go. So now it is debugging this port. And good. Wait, what's going on? I think it's taking a while. Hopefully it's fine. So there we go. Okay. So the issue that I actually totally forgot about because I skipped through it. So remember, so our ESP32 actually does not yet have the ELF file on it. So that was the issue I just had a second ago. So, okay, so the question now is how do we get this .elf file that we've downloaded, how do we get this now onto our ESP32? Well, what we could do is we could probably just use like most of the files that have already been generated for us from this like Blink example. Because like we know that the Blink example can properly put code onto this. So let me go and just close out of this for a second. So CD back into Blink. Okay, and if I now go and just build this project, so there we go. So I built it ahead of time, so it went a little bit quicker. But okay, so I just built this. But now if I go and search, so if I do find, and then look for any files that have a .elf extension, then cool. So we can see, like first we see our lab2 image.elf that we downloaded, but we also see this blink elf. This blink elf is actually the elf file that was generated by this project, by all of our C files. So what we could probably just do is just go in and just overwrite this file with our new file. And if we do that, then I think it will end up kind of just working. So if I go and copy this file and then overwrite this, so there we go. So I've now copied the lab2 file into the build file. Then I can run idf.py flash. And what this will do is it will realize that something has changed. So it will actually rerun some parts of the CMake like project. So you can see, yeah, so it like needs to generate this bootloader.bin and generates things. It realized that something changed. And now we are successfully running the like blink, our like overwritten blink thing. So now if I go and hit monitor on this, then there we go. We can see that we are running this elf file. And we can see that it says that the result of compute is 37. So that's how we can tell that we are running our elf file that we downloaded from the GitHub project. That is what this elf file does, is it just kind of prints out like the result of compute is 37, returns this over and over. And the goal for you is to figure out why it produces this print statement right here, the result of compute is 37. Okay, so now we can go and run OpenOCD and need to connect to this. So I'll go and quit out of this. And I'll just do this. Cool, so now I'm back in Blink. Now I can run open OCD. So good. Now we can see it is opening. It just opened port 3333. So now we can run GDB on this and it should work. So I will do I have it handy? I don't. Okay, so I can find it again with risk 532 and then GDB. And then I can go and pass in this lab2 image.elf. And now in order to connect to this port, now I can go and connect to the device. And there we go. So now this should work. No, what is going on? Okay, well, see, like last time I taught this class, I was like, I'm not going to do a demo of this because it's too finicky. And then this time I was like, I think I can do it. And then it's not working. Well, oh, I just need to run it twice. Okay, cool. So now I've connected to it. Great. That may be your solution. Okay. Now what I'm going to do is just run a couple things. Now I will also go and restart the ESP32 because the ESP32 like already was running. So I'm going to run mon reset and halt. There we go. So now it is halted and it's at the beginning and it's not yet run anything. And then I'm going to flush all of the registers and flush the cache with this command right here. These are all provided on the website. So there we go. Cool. So I've done that. Now the question is, well, how do we now stop execution? Like if I now were to just hit like continue, then it would run through our entire program and it wouldn't like stop. And it would probably just like, I don't know, freeze and run out of memory or something. So the question now is, how do we get it to stop running right as soon as it reaches app main? Okay, so what we could probably do is just add a breakpoint where we do breakpoint and probably just app main. So let's go and run this. And okay, cool. So we have done this. Well, if you have like an incredible memory, you'll actually note that this address appears to be incorrect, which is odd. So I'm going to go back to this elf file that I dumped right here. And so if we look at app main, so we can see the address that this exists at. It's at this address, which is quite different from the one that it reported. It reported this address, which is like all the way down here. I have no idea why it's doing this. I like have looked up a bunch of things and I have no idea why it's doing this. This is a bug that I'm certain all of you will face, where if you try just doing break app main and then run it, it will actually skip like all of the important code and then it'll hit an infinite loop and it'll break and won't work. So what you will need to do is actually go and instead of doing a breakpoint on app main, instead what you will need to do is put a breakpoint on this like physical, like on this address instead. So you can't do a breakpoint on app main. Instead, you need to do a breakpoint on that address. And the way that you do a breakpoint on an address is you do B. B means breakpoint. And then we can do star to dereference pointer. And then we can do this address right here. And there we go. So now we have the breakpoint properly set up. And now if I go and hit continue, then we should see that it actually hits the breakpoint. Cool. Now it is our goal to kind of single step through this and try to figure out exactly what's happening. Okay, any questions at this point? Okay. Yeah.
Wait, so you said we could do this on like a WSL basically on
Yeah.
our own computer?
Yeah, I'm just on my computer. Yeah. Okay. So what I would also recommend doing is like if you are having trouble like using GDB, I recommend just like asking Google, asking ChatGPT. That'll probably be the best thing. But if we want to just like start single stepping through things, then well, it's not working. That's okay. Well, you can just kind of experiment around with this. Debugging for microcontrollers is just a little bit trickier than debugging for like a regular computer. And then an additional issue that they have, or an additional issue that this lab assignment will have is now you don't have access to the actual source code. Instead, you have to deal with this like .elf file that we gave you. Maybe it would have been better if we just gave you the source file and then you could like debug it that way. But we thought it'd be kind of fun if we gave you an elf file and then you'd have to like really think about what an elf file is and then think about like the build system. So there we go. That should hopefully be enough to kind of get you started on debugging this homework assignment. And now, yeah, all you have to do is just figure out like actually what the process of this code is and figure out what is happening and then answer the questions that go along with it. Yeah, question. Exactly, yeah, S is single step. You can look up like cheat sheets on GDB. I don't have time to go over it right now, but GDB is the most common application that is used for debugging C and C++ programs. And there's tons of resources on there. Yeah. Okay, any questions on anything? Yeah. Thanks for being patient as I was debugging some stuff. We got there. Okay. Cool, well, that is also on Wednesday. We will continue talking about Lab 2. Feel free to come forward with any questions. But yeah, I look forward to seeing you on Wednesday.